The method we're going to look at in this class is named after this very famous German mathematician. His name is Leonhard Euler. And it is a common mistake among students to call him Euler, but actually, because of his ethnic origin, his last name is actually pronounced Euler, just like the Oilers, yes. And for those of you who are Flames fan, remember that his work is like a flame for mathematics, so he's a pleaser for both sides. But let's go back to the method. What is the method all about? So far, we've tried to solve differential equations, and we have seen a few we haven't developed them ourselves, I wish, but we have seen some methods to solve certain differential equations in certain particular situations where a method was easily implementable, a certain method. But there are some situations where those two methods, namely separable and linear equations, neither of those two methods works, and we may still need to solve the differential equation. In general, this is a very hard problem in mathematics, and it is still work in progress. There are still mathematicians who are looking at different kinds of methods, or for solving either large classes of differential equations or even special cases. However, there is one situation in which the solution can be obtained numerically, that is approximately. What am I talking about? Okay, so let's say that we have an initial value problem. Notice that we need, in order to apply this method, we need to add also the extra condition. We're going to do a numerical solution, and therefore we need to have a place to start from with our calculations. But let's say that we cannot work it out algebraically, just by doing algebra, integrating, and so on. In some situations, as I said, we can get a numerical approximate solution, and this method is one such situation. So let's see what this situation is. Now notice once again that just like other kinds of differential equations that we have seen, they only work under certain particular conditions. The good thing about this method is that the condition it requires is fairly mild, and so you're going to find that it is useful in many situations. So let's have a look at that. So what is the basic idea of Euler's method? Well, first of all, we're going to be looking at an initial value problem that is of this form. The differential equation can be written in the form y prime equals some function of both x and y. So what I'm saying here is that we need a differential equation where y prime can be isolated. Now, what is y prime? Of course, we know as usual that y prime is the derivative of some function of x. And then on top of that, we're going to have some initial condition. So y of some initial value x0 is going to be some number y0. Under this condition, what we can do is we can construct an approximate solution, which means we're going to construct a table. We're going to construct a table by building up points on the solution. Remember, the solution is supposed to be a specific function, right? So instead of giving the function as a formula, we're going to give it as a table of values. So we're going to build up a whole bunch of x values and the corresponding y values. And how are we going to do that? By using, in fact, a method that we saw in the fall term. Well, I'll tell you in a second what that is. Here it comes. So notice that at this point we do have a point. We have an initial point. Remember, that's a given. And we also have the slope of the function we're looking for, right? Because we have the derivative written explicitly as a function of x and y. And if we have x0 and y0, we can figure out what the slope is at that point. Well, if we have the point and the slope, what can we construct? Well, we can construct the tangent line, or what we called in the fall term the linear approximation. You may remember that the formula for the linear approximation goes as follows. If we're looking for the value of the function near the point x0, so at some point x1, which we're going to take to be x0 plus a little bit, this is approximately equal to the value of the function at x0 plus the value of the derivative of the function at x0 times the little h that we're adding. Now, if you're lost familiarity with this formula, you may want to refresh your memory on it, because of course this is going to be the crucial part of the method. Now notice that f prime of x0 is just y prime at that point, and y prime is given by the formula capital F of x and y. So in other words, we know what y prime is, and it's given by capital F of x0, y0. Okay? So if we apply this formula with the beginning point in mind, what we're going to do is we're going to get an approximate value of this f of x1, which we can call y1. Okay? So at this point, we now have another point on our curve. We have x0 plus h, and then we have the corresponding y value, which we're going to call y1. Well, but now we have a second point. Why not repeat exactly the same procedure, right? So what we can do is we can use this new point that we have obtained and use a linear approximation, same formula as before, to get a third point, which we're going to call f of x2. So this is going to be equal to f of x1 plus a little bit, which is approximately f of x1 plus the derivative at x1 times h, which is equal to y1 plus, remember, y prime is given through our formula, capital F. So we can use that one and get a third point, y2. Now our table is starting to become more and more rich of points, and if we plotted these points, which we're going to do soon, we can get an idea of what the whole function will look like. Well, why stop now? Keep doing it again. So what we can do is, and now can use this third point that we have obtained, apply the same formula to it, go through the same steps, and come up with a fourth point. Okay? So we end up with this fourth point, and we have its coordinates. And of course, we can keep going. So what we can do is we can use this formula and repeat it as many times as we want until we have enough points to have an idea of what the solution looks like and get an approximate idea.